and here's the master thesis defense. Actually, funnily, 3 years of work.
In 3 years.
The first year was highly exploratory. The second was a little less exploratory. And the third year, I guess, was just super focused and diffused on a totally different.
Completely different thing, but it converges back on the work, so it's okay. Okay, so tangent over. Welcome, everyone. Thank you so much for coming to my master's thesis defense. My thesis is called Toward Formal Verification of a Lock-Free Distributed Double Buffer Cache. We will detangle what those words mean. My name is Mike Doan. I'm from the Department of Computer Science at Georgia State University, and here are my committee members, Dr. Sophie Pliss, Dr. Raj Sudaraman, and Dr. Liping Wan. Okay, so first of all, what are we doing? So the original motivation for this project was a genuine, like real data problem in neuroimaging imaging. The issue is that deep learning requires large labeled data sets in the order of hundreds of thousands. Brain MRIs require expert annotation, which is expensive and very slow, so there's not many of them. And a state-of-the-art data set for neuroimaging might be somewhere in the order of a couple hundred to a couple thousand data points. Not enough to train a model, so you need something that looks like synthetic data. So you generate labeled samples on the fly, and approaches like SynSeg, SynStrip, MindGrab, all of these models are trained on synthetic scans. Issue. Generation might be very slow. In Billat et al., which is the SynSeg paper, it took them 7 days on one GPU to get 300,000 scans, which is like about the ballpark of what you want for a pre-trained model. If you calculate, because MRI samples are cubic spatially, and in total they are, it's 4-dimensional because you also have the channel dimension. So 3 spatial and 1 channel dimension. And for 300,000 samples, that's 366 terabytes at full precision. All of it synthetic. That's, who here has 366 terabytes just like laying around for a single training job of a bunch of synthetic data? And so it's not really feasible to do this at scale. 7 days. This means that there's no time for architecture search, no hyperparameter tuning. The model was actually pretty small. You can tell because it fit on one GPU. I believe they trained on either A100s or V100s.
No, they trained on the 6000, the one that
A6000? 80 gigs. Okay. So still only 80 gigs, not those newfangled. Yeah, not the newfangled like B200s, like 144 gigabytes of RAM and so on. So these are moderate sized models, but 7 days means that it's just like not really feasible to do sweeps of them. So the result is that it's just a regular UNet, and so they didn't have the room to actually explore different architectures like we did for the original Wirehead paper. So the solution, we need to make generation fast without storing anything. So this is how the loop approximately worked for SynSeg. They generate a sample, they got some data, they train on it, they calculate the loss, and then they update the model, just like in a loop, right? And it's completely blocking at every phase. So you don't train until you get the sample, and you don't update the loss until you're done with it, and then you don't generate the next one. So obviously there is, there's a lot of headroom for optimization, because why aren't you doing generation at the same time that you're doing training? Like, why aren't you doing multiple generations while you're doing training? The issue though is scheduling. So that was the solution that we came up with for Wirehead. This is the final version of Wirehead that will be presented.
Sorry to interrupt.
Yes.
So why there's an echo?
Is there an echo? Oh, is my speaker coming?
This side we can hear it clearly.
Yeah, we can hear you on this side.
Okay, so you use a model to generate the images, right? And then
it is, yeah. Go ahead.
And then you use the synthetic images to train a model.
The generation process is not model based. It was a static process. It just took the sample. It trained a Gaussian mixture model on it, and then it sampled from it to create things that looked like brain scans. So it wasn't actually a neural network. It was just a deterministic process that was ran on the CPU.
Well, it's probabilistic, but it's a different model.
Yeah, it's a different model, but yeah, it's not coupled with the model that we trained. It's completely frozen.
Yeah.
Okay. So I'm not very familiar with this, but to me, if your data is generated by a model and then you use that model, you use the data to train another model, I, I don't know. Okay.
Are you concerned about overfitting or like not generalization?
Yeah, something like that. Seems like you're the model you train will learn, or is it general enough, or it's just gonna, yeah, it's
So
overfitting.
yeah. That's a very fair concern. That is a major point of concern in every single paper that ever used synthetic data in this domain. SynSec had to go through the same critique. MindGrab and also our paper also had to go through the same critique. The solution or the answer at the limit is probably not. It doesn't actually overfit. We evaluate entirely on real data. So we do not evaluate the models on the synthetically generated samples. And the generated samples are completely independent from the data we evaluate on. We like MindGrab, a future work for or like a, what would MindGrab be? Like a successor work, like a follow-up work?
Well, I mean, it's a use case. It's an example of this.
Yeah, in MindGrab, we trained it on the same data that was used for. Do we use on same data for Wirehead? Like the same generated? Yeah. So it's the same data that we use for Wirehead, but the samples that we evaluated on were baby brains, which were completely out of distribution.
Not just baby, a lot of 20, not 20, about 10 different data sets, very different, never seen by the model.
Yeah,
it's called domain randomization. That's what we're doing, and it actually creates robust models that are way robust.
We can jump back to the point on data. It's pretty much a cell question for the original Wirehead paper. It's been like proven multiple times that it does actually generalize.
Yeah, it's not part of.
Yeah, not really part of this specific this thesis. Yeah. So with the decoupled architecture, I will explain briefly how it works. You have two buffers. The first one is a read buffer, and the second one is a write buffer. You can have as many generators as you want. So Gen 1, Gen 2, Gen 3, and so on. These are the things that make the data, and they push concurrently, like out of order, to a write collection. And when this thing fills up, a swap will trigger, which switches it to the read collection. Now, the swap here does not actually move any data. It only swaps the label or the identifier for the collection. And so it's all in place and it's done atomically. So it's done instantaneously. There's no processing, there's no data movement being done. And from the perspective of the training job, it's pulling from the same place every single time. And the swap operation happens in such a way that the read collection never gets corrupted. So any questions regarding this point? This is like the core of the algorithm.
So generation wrap. So when you generate like the 12 here, you generate 12 and you send 12 there. Not you generate one and send one.
Can you say that again?
Like for you generate 12 images, like just images, and then you send the 12 images.
Oh, no. Every generator just pushes their sample. They don't even care where they're pushing. They just know I'm pushing to a place called write, and it will go there. It doesn't know what's in the collection, nor does it care.
It doesn't have to be waiting for the.
No, it doesn't. Yeah. Everything is completely independent.
So you updated it recently, because when I was using it, I have to wait for the whole batch to finish.
You don't have to. From the perspective of a single generator, you wait for your generation process, but across the whole system, there's no waiting. Yeah,
the write collection needs to be filled up first time before the training starts.
Yes. Otherwise, you won't have anything to read from. The data integrity happens during the swap. So until there's a swap that happens, you can't read anything. But that's to be expected. Like you have to fill it with the first collection first. Okay.
So are these two buffers in memory?
These two buffers are in memory. They're stored in MongoDB. We host them on the Arc18 node on the Trends cluster, which has a terabyte of memory. So everything lives in memory. You can make them as arbitrarily big or small as you want. The only thing that affects is the frequency of swaps.
But the data is generated. The images are generated by the GPU, right? You run the.
It could be either CPU or GPU. For the original Wirehead.
But if it's generated by the GPU, then the data will be moved from the GPU memory to this write buffer, the MongoDB buffer, right?
You can route the networking in however way you want. Because it was in CPU, we had to route through system memory. But if the generation process happened in GPU, you can actually move it through NVLink.
No, but the question I think is that this is all happening in the network. There are different nodes.
There are different nodes.
Everything is different nodes.
Yes, everything is in different nodes. You could have it be on anything you want.
I see.
Yeah.
Okay.
Okay.
I have a question.
Yes.
When we are generating data using a Gaussian mixture model, I'm thinking about maybe about MRI data. It's not correct, but like about text or image. If you randomly pick a point, like understand the distribution using Gaussian mixture models, and pick a point like in text, maybe we are picking something that there is no, like a word related to that in our dictionary, right? So how is there any strategy or something to understand the data is rational or something?
That has to be done on a case-by-case basis for the generation process. But Wirehead itself is only
okay.
It's just a data structure.
We work with this is not about generation. Generation could be any, like you can run what is it called? I forgot. But there are finite element simulators that simulate in MATLAB. Like you can do that. It's like whatever your problem requires. We don't care. The problem here is that generators are slower. In our case, they're only it's like 8 seconds versus a millisecond for training. But in your case, it could be hours or something.
So in this example, you have 4 generators, right? And I thought they were on GPUs, but you actually listed them on CPUs. So are these generators running on different compute nodes, or
yes, they can run on any they can run on anywhere, so long as they can reach the MongoDB instance. It can write into that collection. So it doesn't have to be on the same node. All of these are actually happening on different nodes, and in the original Wirehead paper, they were happening on 20 different machines. I've scaled up to over 200 processes, and it still worked just fine.
So in your implementation, basically, the multi-thread, or multi-process writing, right? So basically, you have multiple processes writing data to the buffer, right? It's handled by MongoDB, right? You didn't do anything, right?
What do you mean? It's handled by MongoDB. We use MongoDB as the data store in a similar way where you can use like the file system as a data store.
You're saying you have a buffer, right? You write the data to this buffer, right? And you have multiple writers, and they can write the data concurrently to that buffer, right? So how do you manage that? How do you manage the concurrent parallel writing?
Yes. So some parts of it were handled by us, and some parts of it are handled by MongoDB. At the at the bottom level, MongoDB works with collections. Tiny collections, they have a size limit of 16 megabytes. So within that scope, we have guarantee of atomicity. However, because our data samples are larger than cubic, they're actually 64 megabytes per sample. We have to chunk them up and implement another coherence protocol on top. That have to be checked both ends.
Even tell about threads is a disaster as well.
We'll get to Redis in.
Okay.
Yeah, we'll get to Redis in a second.
Just let you know slide. You can answer everything right here.
Yeah. So the generators aren't sending an entire sample over and relying purely on the MongoDB atomicity or like transactional guarantees. Because the samples are way too big, we actually have to chunk them up and recreate them on the other side. There's a mechanism we call telomeres that signal when a sample is actually correct. And there's a proof in the formalization that says that when the swap happens, every single sample on the read collection is guaranteed to be correct. So it's a statement about the correctness of both the writing operation and also the read operation. So MongoDB only guarantees within a small chunk, similar to like how TCP guarantees you. But packets are guaranteed, but the whole document, you still have to have your own correctness guarantees on top. Does that answer your question, Dr. Wen?
Not exactly, but that's fine. Let's just move on.
Okay. So in terms of results, the coupled version for Synsec, while we benchmarked it, it revealed that the slowness of it was entirely due to the fact that the generation process was blocking the training process, exactly equal to the batch size. So every single one of those spikes is just a spike in the utilization for like Synsec uses the GPU a little bit. And so it spikes the GPU and then spikes the GPU. And then the training job is that long streak. And because it was blocking on every single step, it only achieved 34.8 GPU utilization. Whereas for Wirehead, this was for the original version published to BHI, it achieved 87.5 utilization. And this was with a ratio of 16 to 1. So 16 generators to 1 trainer job. Yeah. And we achieved a roughly linear increase in throughput. So 16 generators gave us 15.7x in throughput from 7 days down to just 9 hours. And in terms of training quality, this answered your questions a little bit, Dr. Wen, on whether or not the generation process being from a synthetic source could make the model perform worse. And the answer is yes, if you don't change the data. So in the case of the coupled generation process, the data ratio was 1-to-1, so 1 trainer to 1 generator, and train and eval scores rose roughly monotonically, like at the same rate. For the local generation job, where the ratio is also 1-to-1 for Wirehead, because the throughput is increased, the ratio is now no longer 1-to-1. There's many more samples being generated than there are. What is it? Huh? Oh yeah. There's many more samples being trained on than there are data sources, and the result was that it overfit. So train rose very fast, but the eval flattened. For the distributed case, where the ratio was 16-to-1, the train and eval like almost perfectly matched up together. So it rose in lockstep. Very interestingly, eval has a higher score than train. And this is because the synthetic samples are so noisy that fitting them is a harder task than simply learning the like the real distribution. Yes.
Eval is on real data.
Eval is on real data, yes. Yeah, so train consistently got a lower score for most of the training job. And eval was actually higher for many segments.
That's expected in this.
Yeah.
Even though it's counterintuitive.
It's counterintuitive from the normal perspective. For synthetic data, this is usually what happens, because you can arbitrarily make the training data as hard as you want, and the eval tasks are fixed, so you can always like shift the curve up and down. Okay, so the algorithm itself. This is pseudocode in a minimal Python implementation. The buffer itself has a, let's call it the Wirehead del buffer. It has a size. So this is also called the swap cap. How many documents or how many collections do we hold until we do a swap? The IDX is the current index for the write. And you have 2 collections of lists, which are write and read. And the swap lock is just the usual threading lock that's provided in Python. The put function is the function which writes the data to the write collection. So you obtain the lock, you write it, you bump the index up, and if the index is larger than the swap cap or the size of the collection, then you initiate the swap lock.
Okay, so I think this basically answers my questions, right? So basically you have your own code to handle the multi-thread buffer write, right?
Yes. Yeah, the multi-threading of everything is handled primarily by us. Mongo only takes care of the correctness of the chunks.
So basically now you have multiple writers, and now basically they need to write data to the same buffer, and you have a lock, right? Which you know, every writer needs to get the lock before they can access that buffer.
Yes, in Python, they need to access, so like locally in Python, you need to access an index lock. For the real implementation, there is no index lock. Every sample only fetches its index and then writes to it, but it doesn't wait. It doesn't require like a special index lock. It's only locking on the swap operation. That's the only place where mutual exclusion happens.
Oh, so you're saying basically every writer is assigned a dedicated memory space?
No. Yeah, they just fetch an index like yeah, the first guy fetches 0, and then the second guy can fetch the number 1 right afterwards. So it just increments on the MongoDB collection, but neither writer is waiting for the other to finish their job.
I think
that's what I said, right? Every writer has a dedicated, you know, ID or something.
Yeah, they have a dedicated ID, but the memory space is completely independent. They actually push their collections interleaved. So yeah. So we only lock on the ID and not the memory space, because this makes it so that the writing process can be as concurrent as possible. Imagine instead that we wrote, or we waited, and then we wrote all 4 of the small chunks to Mongo one at a time. So writer 0 has to push all 4 chunks, and then writer 1 can push its 4 chunks. But that can't saturate the bandwidth fast enough. What you actually want is to interleave the writing processes.
So basically your IDs are multiple locks, right? Each ID is a lock. So you have
each ID, it's not a lock on the writing process. It's only an identifier for where the writing happens. We don't lock on the ID.
No, it's, you know, I think it's kind of a lock. So basically you have a pool of locks, right? So as long as you can get an ID from that pool, you kind of get an ID. It's kind of like you get a lock that you can write the data to the buffer.
You don't, because you can actually we actually allow having more IDs than there are spots in the collection.
Oh, well, I can explain add a little bit to that, because we completely decoupled training job from this generation and data store. But from training job perspective, it has an epoch. And in epoch, the data IDs, the sample IDs, go from 0 to the size of epoch, which is, say, 1,000. And when training job is happening, it requesting random, according to its sampler, batch size random IDs. And from its perspective, there couldn't be duplicates of IDs, shouldn't be any duplicates of IDs in the epoch, in the database, in the training. So that's why we are looking on IDs. So the IDs in one entire buffer are unique and sequential and everything, because the trainer has no idea what we're doing behind the scenes. The training thinks it's training. The trainer, by the trainer, I mean the framework, PyTorch or whatever does it. They think they're training from a static database. Yeah, from a static data set.
Yeah. Well, the thing though is that we don't actually lock on the ID. We can actually have holes in the ID perfectly fine. So imagine the swap cap is 100. 200 IDs can actually be obtained by the writers, and you could have holes of like 50, 60, And then during the swap, it actually re-indexes the ID so that they become contiguous afterwards. So it's completely lock free from the ID's perspective.
Well, oh, okay.
Yeah.
So you're saying you can have more IDs than the actual, slots in a
Yes. Yes, because the ID only tells, from the perspective of Mongo, an ID being obtained is only saying that there is a writer attempting to write to this ID. It doesn't say that there is a sample here. Yeah, you need to obtain the ID first.
And it's not Mongo's structure; it's our.
It's our structure.
That's why we can violate it.
Mm-hmm.
So let's say in your buffer you have 100 slots, and now can you have more than 100 writers write data?
Yes, you can. Yes, you can. Yeah, and then whichever 100 collections are wrote to completely first, they are swapped.
Okay, so basically let's say you have 200 writers, right? Those 200 writers will compete for those 100 slots.
They don't compete for the slots. They fetch 200 distinct IDs, and then they write to them, and whichever samples complete first.
Who decide which writer gets which ID?
The ID is assigned via an atomic increment operation on Mongo's side.
It's randomized.
So it's not randomized. It's just incrementing. It's just like a simple.
Yes, but the access is more of like Ethernet. Try, wait, and so.
No. Because it's only incrementing a single integer, it happens light
like
speed. Yeah, it happens basically light speed. So there isn't like real contention on the ID. The real contention happens on the writing of the samples after the IDs are obtained.
No, but we don't care about that. We don't handle it.
We implicitly don't handle it. Yeah.
So the writers which didn't get a chance, their samples are lost, or will they generate?
Yeah. Well, whenever 100 samples are completed, whatever sample is still in flight, they get thrown away. Mm-hmm. So there could be waste, but you could easily like change the ratios of the writers so that as few samples are wasted as possible. Mm-hmm.
Okay.
Go. And the read is very simple. Read just reads from the ID respective in the read collection. There's a tiny bit of concern to be done because you should verify. There's a verification thing for, how do I say this? Because reads cannot be atomic, you have to pull multiple chunks from Mongo. There is an edge case, which is that the reader can read some samples and then the swap can happen. And so the read collection is deleted, and now you have like missing samples for the rest of the chunk. Like packets. Yeah, it's packets. But so that's the responsibility of the reader. Yeah. So the reader has to implement a correctness algorithm to check if the chunks are actually correct, so that it doesn't read corrupted data, basically. Go. So the life cycle is that the generator starts as the ready state. It attains an index, which changes it to a has index state. It moves to insert, which is just like it finished the insertion process. Try and swap is another state. In swap is another state, and then it goes back to ready. These states are modeled as inductive cases in a inductive type. So the type system for Rock can actually model this state machine natively. So there's no need for like flags. These are not Boolean flags. These are inductive definitions that are swapped in between function calls. So these are like completely correct. You cannot have a generator that is simultaneously in.
Too fast into theory improving. You didn't give us a chance to understand.
Okay. So before I move on, do the states make sense? Yeah, ready just means nothing's happening. It's like an idle state. Has index means that it has obtained an index from Mongo. Inserted means that it has finished inserting all of its samples into Mongo. And then these two are conditional. So whenever the data set is full, whenever it detects that the number of inserted samples is above the swap cap, it will try a swap. And I've tried to obtain a swap lock. If it does obtain it, then it swaps to this very fancy state called in swap, which is another fancy thing. And then once it's finished with the swap, it goes back to ready. Does that make sense? Yeah. The difference is that these are defined implicitly in Python as part of Python's normal control flow. It's just like a big function. But in Rock, these are defined as inductive cases. So like for the natural numbers, a natural number is either 0 or successor to some number, right? And you cannot have a natural number defined inductively that is both 0 and the successor to some number, right? So this is correct by definition. And similar here, the generator here is mutually independent by definition. You cannot have a generator that is in two states at once. It can only be in one state. Does that make sense? Okay. Okay, wonderful. Yeah, so claims an index via atomic increment. It writes a sample. It increments the completed collection after it finished its writing process, and then it checks if the number of completed samples is larger than the swap cap. If so, then try a swap. Okay, so in MongoDB, these are the collections. Write, read, temp, counters are the four main collections. At any given point in time, only two of these colored collections are alive. So write is where generators insert, read is where training reads from, and temp is used during swap. Temp is required, yes?
Read is the only collection visible to the training.
Yes, yeah, so the training job only ever sees read.
Stable, it never changes for its person.
Yeah, yeah, and shuffling between these three collections happens only, it's basically a swapping of pointers. There is no data movement happening in between these three collections. You can also model this as read is guaranteed to be consistent. It's guaranteed to be in order. It's guaranteed all the data is supposed to be correct. In write, everything happens out of order. There's no considerations for any concerns whatsoever. It just happens completely out of order. In temp, temp is where the write is validated. So we've proven now that the collection cannot have anything wrong happening to it, but there is a post-processing step that happens during the swap. Basically checks if the telomeres for the samples actually match up to the data points they say they're from. So if I have a telomere for sample 5, you have to check, are the rest of the samples for sample 5 actually present? Yeah, and if this isn't true for all the telomeres in the temp collection, then it can be thrown out.
The training doesn't know this is happening.
Correct.
It's happily continues all that time.
Correct. Yeah. So while all this stuff is happening,
full decoupling.
Yeah, completely coupled. During all this process, the trainer just pulls samples. It doesn't even know where it's from. This happens to line up perfectly with the statistical assumptions we make in machine learning. But otherwise, you might have to impose like more constraints. But for machine learning, you don't care. So you just read samples as you go along. And the counters collection is where we keep those IDs. So started is the index that we pull when we start the writing. Completed is where the telomeres are slapped to. So it just like appends the number. And swap lock is the single bit that just tells you, hey, there's someone taking over the swapping process. One of the key insights that we used for removing the manager process. So there used to be a very large like manager process that would have to be bundled in with the wirehead job. And it was very problematic because if you had two managers, then they could step over each other. So what used to happen was that the swap lock was held by the manager. But if there's two managers, now you have a huge issue, right? So eventually I realized that you could actually use the lack of a write collection as a mutex. And the mutex for what exactly? Mutex for the runtime of the generators. The generators only switch between states like this whenever there is a write collection. Yeah, So this removes the need for an explicit manager collection. Every writer can now run completely independently without having to wait or to be blocked on an external process. This also makes distributed deployment much more easy because it's plainly just however many generators you want and however many training jobs you want, completely decoupled. You don't need to check if there's a manager alive.
It's better.
It's better.
It's better.
It's way better
than you described.
Oh.
Because you can add and remove generators while everything is happening.
Yes. So
and
that's
you can
yeah.
change your settings for the generated data while it is happening.
Yes.
And you can remix your parameters while the training continues.
Yeah.
And you can see the learning curve, and on the fly you could decide that it's plateaued, the data is too hard. Now let's make it a little easy. Even either mix in new generators or kill the old generators, start the new ones. Nothing stops.
Yeah.
The process continues. And, it's very hard to kill.
Yeah.
So training only pulls from the MongoDB and whatever is happening by the script, it doesn't really affect.
It does not affect the read script at all. Yeah. It is guaranteed after the first swap that there's going to be a read collection always. So you always will be able to read and you'll always get healthy samples from it. Okay, so the 7 swap steps. There we go. The first one, you rename the write collection to a temp collection. And then the second one is you drop the write collection. This activates the implicit mutex and stops the other writers from trying to trample over your job. And then third step is you validate the temp collection. So this is where you check that the telomeres correspond to the samples that it says it corresponds to. Then, if it succeeds, you rename the read collection, the temp collection to read. Now, notice that this renaming actually overwrites the original read collection. So when you do this, the read collection or the original read collection gets dropped, but it happens atomically because it's only swapping a pointer. So from the training job's perspective, it's still just pulling from the read collection. It doesn't even know that a swap happened. Or if the temp collection failed, it cannot happen in the model that we have in ROC, but it can happen in the case of the real wirehead when the generators die. We don't model process failure in the formalization. Okay, and then to get everything going again, you create a new write collection, which releases the mutex, and now everything can happen again. And you reset all the counters so that you start writing from index 0 and then a number of convenient samples.
My understanding is during step 2 to 5, the generators have to wait, right? They cannot.
Yes, they do. Yeah, they do have to wait. But the generators wait. The read collection does not.
Right.
Yeah. So the writing process is blocked. It usually happens between 1 and 2 seconds. The newest implementation happens basically instantaneously because the verification process, it only checks the presence of. It doesn't do any fancy like checksum. So data, because we can lay off data correctness to Mongo, we don't have to do any fancy checksum. It only is checking like a couple hundred identifiers on MongoDB, basically, which can happen instantaneously, like effectively instantaneously. Okay, we are way behind schedule, so I will speed up. Why formal verification? Because Wirehead went through about I'm counting like 6 different rewrites. Starting with the first version, which is Redis, there was a single buffer and there was no swap process. Everything pushed and everything pulled. The issue is that Redis has it has a global lock on all reads and writes, and you can actually choke out the readers because if you have 20 writers and only 1 reader, the ratio of reads you can do is 1 to 20. You can only do 1 read every 20 writes because everything is happening on a single thread effectively. So that one only worked for scales, I think up to like 3 or 4 writers. Like it barely worked. It was correct, but it didn't really work. It was choked out. Then version 2 through version, version 2 is the one that went into BHI. There's 3 components and there's a separate manager process. This is where the swapping thing happened. And then V3 is everything that happened after BHI. So we removed the manager, we changed the locking strategy. The locking strategy was actually incorrect in V3, and it only became correct once we got to V5. And the current design is like the extra stuff that we have on top for making the algorithm much more clean. And every time I said word for word, I'm pretty sure it's correct, but it was ever so slightly not correct.
It's good that we have real users.
It's good that we have real users now, because otherwise I wouldn't be able to make that claim. So there's a quote from Dijkstra, which says the distinction between testing and proving. Testing shows the presence, not the absence of bugs. So you can only verify the correctness up to what you specify in the tests. But because it's finite cases, it's never 100% sure that you're 100% correct. So this is why we want a mathematical proof that covers all interleavings, all possible states that the system could be in. You model the entire system of Wirehead as a giant mathematical function, and then you prove properties about this function. Paper proofs have errors. We want machine-checked proofs. So how do we know it's correct? Yeah, so we have 6 times of writing over 29 months, and every rewrite changed how we did concurrency. Enter proof assistance. Anyone here has ever worked with a proof assistant? You have, yeah. Okay. So there's many of them. You might have heard of Lean, because I proselytize Lean all the time here. But there's also Isabel, there's also Agda, and the big daddy of them all, Rock, is the oldest one. It dates from the 80s. And what a proof assistant is a program. It's a language and a program that you can write things into. And it is expressive enough to express mathematical proofs. So you can prove things about natural numbers. You can prove things about real numbers. You can even prove things about programs. And that's what we care about today. You state your theorem as a type, and then you construct a term of that type, which is your proof. If the term type checks, so say in Python, Python also has a type checker, kind of. It's optional. But if you have a function from int to int, and you write that function, and the type checker passes, you know for a fact that the only thing that's coming out of that function is an integer, and the only thing that's coming out of that function is an integer. So that's one property you can verify in Python. That's a very low order property. Yeah, you can't express higher order logic or like very interesting things, like say the correctness of Wirehead in Python's type checker. That's why you have to reach for these very powerful proof assistants. And this works because there's a very deep connection between logic and programming called the Curry-Howard correspondence. It is a correspondence between functions and implication, between pairs and conjunctions, between sums, type theory sums, and logical disjunction. And under the Curry-Howard correspondence, a type is a proposition. A program is a type. Of that type is the proof of that proposition. So if you can construct, say, a procedure by which Wirehead executes things correctly, that is the proof for Wirehead's correctness. There is no auxiliary structure you need. All right. And type checking is equivalent to proof checking. Here's the full table of things that are correspondence. The full correspondence is called the Curry-Howard-Lambeck correspondence. It is also called Harper's computational tritarianism. Robert Harper from CMU has a great lecture series on this topic. It's a correspondence between proof theory, aka logic, computer science, aka type theory, and category theory. Yes.
Fully isomorphic proof.
Yes, these are formal correspondences. There is a way of transporting between propositions, types, and objects. Note that this is not a full correspondence between everything in logic, everything in type theory, and everything in category theory. It's a specific correspondence in specific kinds of logic, specific kinds of type theory, and specific kinds of category theory. In logic, these are second order quantifier logics. So it's just second order logic, second order intuitionistic logic, not classical logic. For type theory, it is dependent type theory. You could also use the various type theories, like Rock's type theory is called the calculus of inductive constructions, which is a model of intuitionistic logic in type theory. And it has these constructions: function type, product type, unit type, void type, the negation type, dependent product, dependent sum, right? And over in category theory, it's not everything in category theory. It's specifically in locally Cartesian categories, which have exponentials, they have products, they have co-products, terminal objects, initial objects. These things are not guaranteed in all categories. These are only guaranteed in locally Cartesian categories. There we go. Wonderful. And then verbs. These above are nouns. These are verbs. Modus ponens in logic corresponds to function application, corresponds to evaluation morphisms. Hypothetical proofs like assume H, prove J, corresponds to lambda abstraction in type theory, and it corresponds to currying in category theory. So on and so forth. There are many, many things, very, very deep connections. And if you would like to study this stuff, Robert Harper is a great source for studying it. Okay, so this is why ROC works. Why can you write a program effectively in ROC and say that you've proven a theorem in regarding wirehead or whatever? It's because the act of proving a theorem is directly correspondent to constructing a wall-type term, which is proving a theorem. Like it just like fundamentally is. The kernel type checks it. So given that there are many proof assistants on the market, like ROC, like Lean4, like Agda, like Isabelle, what's the difference? So ROC is the oldest, and it used calculus of inductive constructions. It has inductive types. It has a tactic language. It is very old. It's older than probably most people in this room. And
I trust grep, right?
Yeah, grep is also very old, older than probably everyone in this room, actually. Maybe not you, Raj.
No, older than Raj.
Older than Raj?
Grep, you're talking about grep? Come on, I was born in the 50s.
Okay, yeah, we have.
Grep came in the 70s, 60s.
Yeah, about the same. Oh, no, it's more than 60s.
Yeah, and so ROC is like the gold standard for theorem proving effectively. Unless if you have to deal with quotients, which if you don't know what the word quotients are, you don't have to worry about it. You never have to deal with quotients in regular programming. Lean4. Lean4 has CIC plus quotients. We don't need that. However, it's a very young kernel. It has a very nice tactic language. It does have dependent types, and it has extraction to C. So Lean would have also been an equivalent choice, but I have an article or I have a section later on why not Lean4. Agda has dependent types, doesn't have a tactic language, and it's very new by comparison. It doesn't really have support for verifying concurrent programs. And same with Isabelle. Isabelle is really for math, more so than for programming. Yeah, so kernel maturity. Proof trusts reduces the kernel soundness. If you write a kernel, or if you write a proof and it type checks, the question of is this proof correct is equivalent to whether or not the kernel is correct. And that property is expressed as kernel soundness. If there's a soundness bug in the kernel, your proof could be wrong. ROC has 30,000 lines of OCaml, 40 years of scrutiny, and MetaROC is a project which self-verifies ROC within ROC. So it implements ROC inside of itself, and then it checks it. Lean4 is 6,000 lines of C++ and written from scratch in 2011. Issue. The formalization of it in Lean itself found a soundness bug. There's actually multiple of them. And I'll show you an example in a second. Another very problematic thing is called native decide. It hands off the checking of various conditions to the language or to the machine. Like say for integer arithmetic, you can hand it off to native decide and it will run it on the machine. However, this is trusting the machine. And when you trust the machine can actually trick you. And if you have a proof with native decide, you can basically smuggle false proofs into the corpus, basically. This is why Mathlib, the largest mathematical library on the planet, bans native decide. You cannot use it. And so you can only use regular decide. The issue is that regular decide is very slow. You transform integer arithmetic from basically O of 1 to O of n, because now you're chaining through that entire call of successors. Yeah. And there is still open questions for Lean. Agda, similar issue. It has a function called size types. It's fundamentally unsound, and you have to enable funky flags to make it work. So here's, as an example of the kind of things you can get up to with an unsound kernel, here's a proof of the Riemann hypothesis. What you do is you make a function whose result depends on runtime randomness. This is a pure function, right? And you get random bytes. And then you just check whether or not if the byte is above 128. And then you run native code twice, and you get contradictory RFL proofs. REFL is reflexivity, so it just equals something else. And you can derive false. And all intuitionistic logics have a principle called the principle of explosion, which says that if you can derive false, from falsehood, anything follows. So if you can get false, you can get anything you want.
If you don't understand about 50% of what Mike's saying, start with Gödel's book.
Great book, great book. Yeah. And then you can derive the Riemann hypothesis. The funny thing is that this only works 25% of the time. You have to roll the dice 4 times on average in order to get one of these REFL proofs, or get these REFL proofs to disagree. And this is patched with the trusted compiler axiom, which you have to declare in your when you call the lean compiler, but there's still holes in it. And so trusting lean for software is not the best idea in the world, because lean's runtime is also unverified. Coq's runtime is verified. It's verified multiple times. Here we go. And this was a result found by Mario Carniero from 2023. As a tangent, I myself am working on a verification project for lean force type checker in Idris, and it is very hairy. It is not an easy project whatsoever. There are many, you would think mathematical objects are clean. They are not clean in the slightest. They have to handle quotients in a special way. You have to handle propositions in a special way. I will speed past this point because we are out of time. Why rock?
But I think we can take a little.
Yeah. So why rock? Well, rock has a massive ecosystem for verifying software. Iris is a project for verifying concurrent programs. Verdi is a whole organization for verifying things. Anyone here heard of Raft? Raft is a data protocol, I think, invented at Google. It's a distributed systems protocol for, I think, like disk correctness. And the verification of that project was done by the Verdi people. And it took 5 years, I think. Insane amounts of effort to verify.
Even with the tools?
Even with these tools. Yeah, but things are just hard. The distributed programming is just really hard. CompSearch is a verified implementation of the C compiler, and it is used all over the place. So if you've driven a car, the likelihood that, and it has software, the likelihood that it has something compiled by CompSearch is actually very high. It's part of the protocols used for shipping software to a car.
This is the marketing part of Mike's business.
Yes. This all this is marketing for theorem provers. Yeah. And a tactic language, tactics. So technically, what you can do to prove theorems is write a whole gigantic term which corresponds to the type. In practice, though, this is very hellish because you have to write the exact thing from scratch, and that's basically infeasible. Instead, what people do is use tactics. I'll get to an example of using tactics in a second. Program extraction. So Rock can extract an OCaml, and you can use it as a reference implementation. So if I wanted, I could compile the version of Wirehead in Rock to OCaml and use it in OCaml. Beautiful. And OCaml also has extraction to C. So I can now move it to C, and now it's completely portable. It doesn't need a C or a Python runtime. And RISC. It is the most scrutinized kernel available and has a 4-decade track record. Lean and Agda are not unusable for projects whose goal is to increase confidence. The most battle-tested foundation wins. Tactic-based proving. So here is where I pull up an example. This is this proof. And this is VS Code. And it is using a thing called VS Rock, which is an extension that tells you, or that lets you do proofs. The way this works is that I can step through the theorem. So currently, this left window is the proof itself, or the program that I'm writing. The right window is the proof state. So when I stepped from nothing, which just says not in proof mode, over to this lemma, swap invariant initial, it's showing me what I have to prove. It's saying for all global state, the initial global state has the invariant. So if I have a global state that's initial, I have a global state that satisfies invariance. What is the invariance that I care about? The invariance that I care about up here is defined to be either For all process IDs, if it's in the swap process, then the swap lock is guaranteed. So the swap lock is actually obtained. For two, this bracket here means and if there are two for all process IDs, PID1 and PID2, if they both hold a swap lock, then those process IDs must be equal, right? So effectively, this is saying two things. The first one is if it says if a global state is swapping, then the swap lock must be obtained. The second one says for any two process IDs that says they have a swap lock, they have to be the same process. So this says there's effectively only one process. And this lemma is saying that this invariant for any global state is true for the initial global state. The initial global state is just the initialized one. So yeah, there we go. And this proof is very easy because if you think about it, when I just initialize a database, it can't be swapping. And so this clause can't be true. It can't be in swap, and neither can these two PIDs be true. So that's why these two cases for both the left and the right-hand side of the conjunction ends with a discriminate. Discriminate is a tactic which discharges contradictions. So it's just not in a, like this proof is very easy, right? Just steps through, and then you eventually discover this one, in swap ready equals true, which is false. It can't be true. You discharge it, and then it turns into false. Go same thing down here. So that's how proofs work. Does that make any sense? Right? You translate, you first translate the state that you want into a type. In this case is swap invariant. And then you construct another term which says the thing you want. So for all global states, if it's initial, then it must also have the invariant. And then you write the proof. And this is right here, the tactic language for rock. Yeah. And so you have intro, you have split. And notice if you step through very carefully, right? When I do the intro, it creates that GS variable, and that all is the hypothesis that I have. So for all PID, the process ID is in a ready state because it just initialized, right? Ready, if you recall from the slides, is the first state the generators are in. And then you split. When you split, the swap invariant goes from one thing to two things because it's declared as a conjunction. To prove a conjunction, you prove two things, the first one and the second one. And so this first dash right here focuses that portion. And then you just walk through it. Introduce the PID and the HIN for this one. You rewrite all, so you apply all. And then because this revealed a contradiction, you can just remove it. You're done. All right, same thing for down here. Okay, does that make any sense? Do you buy, if I showed you this, do you buy that Wirehead, when it first initialized, can guarantee you the swap invariant, which means that if it's locked, then if it says it's swapping, then there's someone holding the swap lock. And if two things says they have the swap lock, then they must be the same thing. Do you buy that?
Can you explain the connection between this proof and the actual Wirehead code?
Okay, that's a hard one. So the issue.
Just show me. You don't have to.
Okay, yeah. The issue is that this is not modeled in the Wirehead code. This cannot be expressed in the Wirehead code.
Wirehead code is written in Python.
Wirehead code is in Python. Yeah, and that's a complete state machine. It just goes from state to state to state, and it doesn't even you can't even in principle.
But you have taken looked at the Wirehead code and abstracted it into. Correct.
So the port of Wirehead lives in this gigantic file called db.v. V is just an extension for rock.
That part,
yeah. So I translate the document into its own type class.
Yes.
I convert a collection. So a document is a thing with a bunch of metadata.
No, I got it. No, this is the piece I didn't.
Okay, wonderful. Yeah. and then you model the database and you model
And
the.
you import this into the proof.
Correct.
Correct.
Correct. Yes. Yes. Safety imports these, and it says properties about that.
That-
So
no,
a huge trust boundary, of course, is why should I trust this implementation?
that's good.
And these are things that you explicitly declare as part of your
Axioms,
theorem statement.
Yeah.
Your assumptions.
Assumptions are axioms, if you want to call them, right? Maybe. Yeah.
Kind of, yes.
Kind of
Yeah.
like the axioms. Yeah.
Yeah. Okay. There we go. Formalization, data model. So documents, they have a doc ID, they have a chunk ID, they have a kind, and they have is telomere. So is telomere is just like the final one in the document. This is modeling exactly the what's it called? The MongoDB document, which has the 60 megabyte limit on the thing. Yeah. In this implementation, that constraint is loosened. So we only have the assumption that a huge chunk can have multiple documents. We don't say how many. So this proof is correct no matter how you slice and dice the document and no matter how you put the telomere at the end, right? A collection, like the write and the read collection, is modeled very simply as a list of document. So list of documents is the collection. The database is an association map between strings and some collection. So if I pass in the string list, it'll map or read, it'll take me to read. If I pass in write, it'll take me to write. If I pass in temp, it'll take me to temp, right? Counters is another collection. It just has two nats. So this is the start ID and this is the completed ID, and that's a swap block, and that's the thing that's being acquired when the swap is happening. DB state has two things. It has the database, which is the bunch of strings mapping to collections, and it has the counters collection right here. Right. That make sense? It's a pretty simple. Yeah, there we go. Okay. Process states. So the swap step, there are many swap steps. Swap rename write to temp, swap drop write, swap promote, swap validate, swap discard. These are things that are swapped through, or these are stepped through when you call the swap function. So it changes from state to state.
7 you showed earlier in one of the slides.
These are the states for the swapping, not for the generators.
Okay.
So these are the states that are inhabited while you're doing the swap. Yeah, and these right here are the steps for the generator. So ready has index, inserted, trying, swap, and in swap. Yeah. There we go. Global state is the global state that we saw over here in the safety.v right here. GS is a global state. The global state has some DB state, which is up here. So some database and some counters. It has some procs, which is a mapping from a process ID to a generator state. So I pass in 0, I get the first generator. Pass in 1, I get the second generator, and so on. And the swap cap is just the number of samples you write until you swap, right? And that's a global state. There we go. The step relation, a bunch of constructors. So step get index, step insert, step skip, the swapping, step check swaps, step lock success, step lock fail. And then this is the whole bunch of steps that you have to go through to get through the swap. 5 minutes? Okay. I still have a ton more. Oh God. Yeah. So in terms of theorems, or in terms of properties I care about, the first one that I care about is reachability. Because you could write a theorem, but who knows how that actually works? Like when you say for all GS here, how do you know these GSs are actually connected? Reachability is the properties that define that. So you define an initial state. I define a relation called star, which is a reflexive transitive relation on global states. This basically says that all global states are connected to the initial state. And reachable is a property that says for if there exists a global state 0 and it's initial, then whenever it swaps, eventually it is connected back to the initial global state 0. So if it swaps, then it must be connected through some chain back to the initial state. Yeah. So this is saying that between swapping and initial, it has to be connected. There we go. Axioms. Quite a few, or just only 3. Make chunks not empty. This says that when you write chunks, it won't be actually empty. For the telomeres, also, this is stating that if the chunks are written, eventually the final doc has to be a telomere, and make chunks ID is saying that the documents that you write into the collection actually correspond to the ID that you set, because this is effectively, these three axioms are covering for the aliveness states of the generators. The only circumstances where these three would fail is if the generators die. Yeah. There we go. Okay. This is the dependency tree for the project. I've trimmed it down to the core theorems. These teal ones are the theorems, and these bottom ones are these purple ones. I guess these pink ones are properties, and everything purple is just the programmatic definition or the port of Wirehead. So the core theorems I care about are post-swap integrity, which says that after you swap, the read collection is correct. Read consistency swap lock free. This is essentially saying that the read consistency of the consistency of the read collection is independent of the state of the swap lock. Swap neutral exclusion, which says that if you're doing a swap, then you must have a lock acquired and the lock is owned by only one guy. Yeah. And progress is the hardest one. Progress says that under fairness assumptions of the scheduling, the whole system will eventually get to a swap. This is a weak fairness assumption. Right. And the properties we care about, swap invariance is the one we already saw. Yes. Lock invariance means that if the lock is held, it will hold all the way through all the swap steps. Reachability is the one we just saw, which says that between initial and swap, they're connected via the star relation, and fair is an assumption. The assumption says that if something is scheduled, if it has an ID, it eventually will get to push it. This is not always held. For example, for the Redis implementation, this is wrong, but for the Mongo implementation, it's correct. There we go. And everything else, probably not enough time to get into it. 3,500 lines of rock across 4 files, 60 auxiliary lemmas is completely gigantic.
If you don't catch my question.
Yes. Yeah. Too late. It's okay. Very, very autumn. So theorem 1, swap neutral exclusion. Swap variance we already saw, and this theorem is pretty short. Yeah, so it holds initially and it's preserved by all 14 step constructions. If I go to step neutral, oh, it's swap neutral exclusion, not step neutral exclusion. Very simple proof. Yeah, basically you just have to establish that it's true for the initial state. You have to show that it's also true for star, or for the swap, and it's true everything in between. And it's maintained by the star relation. So it's kind of like, anyone here ever did an inductive proof before? Remember back in your discrete math class? Yeah, you prove it for the initial state, or like the base case, and you prove it for the inductive case. This is the same thing, but it's via a custom inductive relation we call star. Yeah, as opposed to successor for the natural numbers. Okay.
You call it star because it's 0 or more steps. Is that right?
It's because step can sometimes not change global state.
Yeah, got it.
Yeah. It has to be reflexive and transitive, not just transitive, because step is not guaranteed to change global state. Yeah. There we go. Here's a very funky one regarding step lock success. Step, by the way, is an incredibly long function, or like a hairy function. Definition, I forget if it's a fixed point step now. Definition step. Is it not in this file? I think it might be db. Step. Nope. Fixed point step. Nope. Okay. I'll find it later.
Okay.
Yeah, it's massive. Okay. There we go. Second theorem we really care about: read consistency swap lock free. Only swap promote can promote read, and swap promote requires being mid swap. Mid swap requires the lock. No lock equals no change. Effectively saying read, if nothing's done to it, is guaranteed to be consistent. The only thing that can change it is the swap promote operation, which changes the name of the temp collection to write. And we prove that the swap promote operation guarantees or retains data consistency. So if we have these three things, then it will be true that the read collection will always be consistent if it exists. Does that make sense? Yeah. Effectively, semantically, this says that the neural network sees a consistent snapshot. It never sees corrupted data. Theorem 3, post-swap data scarcity. Yeah, so after a successful swap, read contains a complete validated data set, one sample for every index, so on and so forth. Training process only reads good data. Bada boom. There you go. Swap completeness, or the swap always completes, which is a statement about liveliness. An infinite sequence of states, one per time step, models every possible scheduling processes. So the execution record is inductively defining all possible states that the wirehead system can go through. So it could be that, say, like 5 of them are trying to get a swap lock. One of them actually has a swap lock and is moving through the various states. That whole, like, all permutations of states by wirehead is modeled by this execution record. Very tiny. The reason it's tiny is because it's inductive. This right here is the fairness assumptions. So given that the system is executing, then for all process IDs, which have some natural number associated, they will eventually be able to push their sample. That is the statement of fairness, and this is a weak fairness. Yeah. Yes. We're going through, and then the next theorem is swap has to complete. Okay. Yeah. Progress. Oh God. Yeah. So here's the big results. Under fair scheduling, at least one generator exists and swap cap is above 0. A swap cap eventually completes. So this means that your trainer cannot see stale data forever. It will eventually see it. Okay. The argument. The ready generator eventually schedules. This is via the fairness assumption. You increment started, writes, and you increment complete. Counters are monotonically non-increasing or non-decreasing. After enough rounds completed, will get to swap cap. You enter the trying swap, and then either the swap succeeds on you, or the lock is triggered and someone else is swapping. So either which way, a swap will happen, eventually guaranteed. Either way, a swap happens. The statement, or like this 5-step argument, seems simple. It required 1,000 lines of proofs. It's just the kind of things that happen. Lock freedom, yeah. It just means that no matter what the state of the lock is, you don't care. So if you can't get the lock, it's because someone else is already trying to do what you wanted to do. You can't get the lock swap, the swap lock. It's because someone else is already trying to do the swap. So what does this mean for the epistemics of wirehead? What does this actually mean after we did all these proofs? This is the trust model for this whole process. The first link and the weakest link, or not the weakest, it's like the most core link, is the rock kernel itself. It's 30 key lines of OCaml, 40 years of scrutiny. Metacock is self-verified. So pretty strong epistemics, stronger than most software all of us have touched, like all over the place, like Linux, you boot it up every single day, Mac OS, Android, all these things. Way weaker than this link. Link 2, the OCaml compiler. Used all over the place. Jane Street uses it. Tons of people use it. It's been used for everything. And so also very strong. Link 3, the model. MongoDB ops as pure functions, faithful for a single node. Pretty simple to trust because this is modeling very simple semantics. Intentionally so because we assume atomicity for the writing processes. Link 4 is the weakest. That the model corresponds to actual reality. This model right here only is true for single node MongoDB, which is true in our case, but this means that we don't model partitions. We don't model replica sets. We don't model any query planners, none of these things. And so if you deploy MongoDB in a wider setting than what is established in link 3, it's unclear if the proofs actually hold, right? But for our use cases, it's fine because a 1 terabyte Mongo node is perfectly okay, right? And then link 5 is the actual execution of the theorems themselves. We have 3 axioms on the user's generator, and it's a requirement on the generator, not on the algorithm. So it's saying that these axioms are things that the generators have to implement, not necessarily a correctness statement for the algorithm itself. So yeah, you're trusting that the generators have a correct count, have a correct index, and a correct telomere implemented. Okay, numbers. Liveness, right? Gigantic. This was not done for the while the first draft was submitted, but then I was like, I need this. And so the project effectively doubled in size. We have 2 admitted lemmas in the progress proof. It's a pigeonholing argument. Pigeonholing is the same argument used in the intermediate value theorem, if you're familiar from your calculus class. We have 0 axioms about MongoDB. Limitations. We don't model crashing. We don't model network partitions. We assume fairness. And we have 2 admitted lemmas regarding the progress proof. Right? Future work, we model crashing. We get an OCaml implementation and we compare it to the Python one. So we test it to see if it's the same. We model replica sets to get correctness about eventual consistency. So if you have a Mongo instance on 5 nodes, then it should be correct from the perspective of all 5 nodes eventually, right? And that's hard because that's not even done in the regular Wirehead implementation right now. And I believe the pigeonholing counting invariant is actually not needed. And so I should be able to get rid of these assumptions. Summary. Wirehead itself is the thing that works. Wirehead is now verified in ROC, and these properties are the things that we care about. Mutual exclusion of the swapping, read consistency of the read collection, data integrity of the write collection, and the progress of the whole system as a whole. Lock freedom. Under fair scheduling, the system always makes progress. And you basically are separating algorithmic reasoning, machine checked, from environmental assumptions, which is auditable.
Well, there is one more, like we eat our own dog food. This trained a lot of models that are live right now on brainshop.org, and many people are using them. And we've published like 2 accepted papers, one in process with the models trained using that, and I spend my Christmas, for example, using that as well.
And great news, to this day, there has not been a single recorded instance of Wirehead failing in product, despite the fact that we've modified the algorithm a bunch of times. This is including all the previous versions.
Doing stuff.
Yeah.
And I know why it's called Wirehead. Why did you choose that name?
Wirehead.
Undergrads are allowed to name their things.
Oh, is that right?
Whichever way they want.
Wirehead is my name.
You built Wirehead?
Yes, I built Wirehead. Yeah. What Wirehead is a thing from science fiction. It's where you engineer a system to reward hack a feedback loop. Yeah. So say I enjoy TikTok reels. I engineer a TikTok maker that abuses my reward function. This is a Wirehead. And so the system can behave like this if you want. And so it's like a feedback loop.
So you let him comment. Okay, that's okay.
It's like in math, right?
Yeah.
We don't call it, what is it? We don't call it tropical algebra. Yeah, we call it actually tropical. Well, anyway, we call it by the inventor name.
Yeah,
usually.
Okay, so thank you all for coming. Any questions?
Looks like there are 2 theses here. One is the Wirehead itself, building the Wirehead.
I mean, Wirehead is already published and peer-reviewed, so it's
already. Okay.
Yeah.
One wouldn't be without another.
That's true.
What is the proof?
Yeah.
Yeah.
So if I ask you which of these 2, the proof of Wirehead or Wirehead itself is the main contribution of this thesis, let's say, I would say the proof, right?
I would actually say the original Wirehead. The fact that I had to make no modifications to the original Wirehead algorithm, it goes to show that it was thought through correctly. Yeah.
I think it's kind of both. And
I mean, you validate with the proof.
Yeah, the proofs were very automatic after I stated them. And so it was a hard from the perspective of like engineering and like effort for the proofs. But in terms of like actual thinking, And novelty, it is the original wirehead that is the larger thing. Yeah.
There is also the thing that we don't take into account is that it's plasticity. Our brains might evolve. So it shows.
Yeah, the project completely changed over the course. Originally, it was just Sergey called me to his office and said, "Hey, we have this generator. Can we make it fast?" So it was just originally an OG, just an engineering project, and then over time, the shape of it revealed itself to be a distributed algorithm. It is a novel algorithm that was not verified or published anywhere before, and now the actual shape of the project is, hey, this is a correct algorithm. Yeah, a correct distributed algorithm. And I don't know, I myself only know of a handful of them that have actually been correctly verified at scale. And so it's that's the contribution of this project, of the thesis. For the original one, it's in revealing what that algorithm is. Okay. So, if you don't have questions.
No, I have
yes.
I have a question. So I'm not an expert in formal verification, but I think my interest mainly focus on the the system and the performance, right? The scalability. So you use MongoDB. May I ask why MongoDB? Or have you tried other database systems?
Yes, we have. We have tried Redis. We found a core issue with Redis being that the locking mechanism in Redis was atomic on both ends. And so we couldn't factor out reads and writes. And the result of that was that you can starve the read process. We also tried RabbitMQ, and then we tried a handful of like smaller like collection style database projects, like Postgres was tried for a little bit, but then Mongo was landed on because it had transactional guarantees, and also because it's already used in prod at Trends. So those are the core reasons. Like it was already battle tested at Trends, and there were existing data pipelines integrated into MongoDB. So extending it to include the wirehead system was the easiest approach. But effectively, if anything had the same data guarantees as MongoDB and the same interface, you could plug it in very easily. The exact amount of stuff that Mongo provides is like relatively small. We don't use any of the like distributed semantics for MongoDB besides data correctness.
So outside of this, to augment the answer, outside of this thesis, just from me, I've started using it in industry, and Mongo is unkillable. It's just such a resilient, it's such a resilient, and it's very simple key value pairs. I know there are other key values, but Redis everyone knows, but it doesn't work. Mongo is unkillable.
Like versus something like an S3 Bax thing or like a Postgres, those don't have as strong of a guarantee regarding consistency and correctness of the chunks.
Another key value for you can try is called RocksDB. Have you heard about it?
Can you spell that, please?
RocksDB.
RustDB?
No, Rocks.
ROX.
ROCKS.
RocksDB. I will try RocksDB. Yes.
So
wonderful.
So it's I think it's highly optimized for write workload. So I think in your case, because now you just run MongoDB on one node, right? A single node.
Yeah.
And you have, how many writers can you have?
I've been able to have up to 200.
200.
And these
people are using it with their own wireheads and their own training jobs. And I often run like multi-GPU training jobs simultaneously on the same.
Isolated benchmarking of that particular node hasn't been done like completely ever, but it hasn't had performance hikes as a result of multi-tenant, for example. And it fully saturates a 8x A100 or 8x H100 training job. So two of them?
At least 2 of them.
Okay, yeah, 2 of them. There we go.
Okay, so is it possible that MongoDB can be a bottleneck? Like if you increase the number of data generators?
So MongoDB is a bottleneck.
Can it
be a bottleneck?
I haven't seen system load on that node ever. Even when I'm intensively using it, I don't know how they did it, but like not.
Or
not
so
on the
maybe the bottleneck now is the training. So you don't.
Yes, that's a much better bet. Yeah, it's the fact that reading is not fast enough.
Yeah,
Right.
We are saturating the GPUs. GPUs are running at full speed, like close to 500 kilowatts.
But from the perspective of Wirehead, they are the bottleneck. Well, bottleneck isn't really the right word. Yeah, because
it's not a bottleneck.
yeah, because
It depends on how many jobs you have. It's a very complicated. It's a
So
mess. I
so
don't know
what if
how we do it, engineers?
well, no, I think that's definitely to be taken into account for. I've had properly benchmarked Wirehead to be a task for a while. It just never came up because it wasn't needed for the use cases we had.
Yeah, we don't know. We haven't done roofline.
You have not done roofline analysis of Wirehead. That will be on a future work as a blog post for China.
And also another thing you can try is to I don't know. So Sergey, you mentioned for the training you're already using 2 GPUs.
I'm using 16 at a time. I'm using 8 usually at a time. 8 A100s.
8 A100. So the training is actually a distributed training.
It is distributed data parallel. That's what usually I do.
Oh, okay. Okay.
Yeah, it's not multi-node yet.
So it's each node pulls a worker number of batches at a time.
Okay.
But PyTorch is inefficient in the sense that it's not parallel. Python has its quirks. It could be pulling while the training is happening, but there is the way it's done is 16 workers or 24 workers for each GPU are pulling between batches and then prefetching to the GPU and stuff like that.
Yeah,
like the regular PyTorch way. Yeah, it's not Mongo is not saturating, but we have a cheat as well, or at least I'm using it. I'm using InfiniBand, and I'm going by InfiniBand.
Well, InfiniBand is what you want to use.
Yeah. But so I don't notice the Mongo somehow does not use CPU. Well, we have 36.
Well, why would it have to use CPU even? It's just moving data. It's not
Well,
running.
I mean,
it's not running
keeping
anything.
Oh no! There is another trick. It's NVMe. The Mongo cache is on NVMe drive.
Yeah, the Mongo instance. The Mongo instance is on RAM, and the Mongo cache is on NVMe. And so it's deployed on a very fast node. And the running of Wirehead hasn't revealed any bottlenecks in the performance of MongoDB itself.
And I've tested this back when we only have V100s on multiple instances on AWS with just different instance, EC2 instance for Mongo, and it was also I don't know what racks the nodes were on different racks and still
and for the record, the instances of Wirehead that we're running, these are 100 gigabyte size collections because the swaps never move any data whatsoever. It isn't impacted by the size.
In 8 hours, we're going through about 300,000 to 500,000 samples. Each sample is 256 cube of.
It's 64 megabytes. Yeah.
64 megabytes.
Okay.
So
I think that the data is not completely in memory, right? The memory. What is the memory size on the MongoDB node?
That is 1 terabyte on that MongoDB node.
1 terabyte DRAM?
No. No. What's the size?
Or the NVMe?
Yeah, NVMe is large. Yeah, it's 300 terabytes or something. But that's.
You said 800 terabytes?
300.
Yeah. Well, maybe 100 terabytes. It's terabytes. I don't know.
Let's fact check this.
Let's fact check. I cannot log in.
So what is? I want to know what's the size of the DRAM and the NVMe on that MongoDB node.
Okay, you want to know? We'll get it to you. Log in. Just
maybe I can use it.
Yeah. It's a different kind of expiring.
I think we should stop the recording. Probably.
Yeah.
Well, I mean, we're not talking about any secret stuff, right?
Yeah, I'm just joking. Yeah, because yeah, I think
Yeah.
there are also some you know, software library maybe you can try. So basically, we don't want to have something like a MongoDB in the middle. So can you just basically the writer and the reader can you know, transfer data from the writer to the reader directly?
They can.
Memory to memory.
It's better to do it in memory. Yes, but this is the data routing concern. This can be configured to happen, like
So
all in memory.
And also it is, yeah, I was too, it's only 6 terabyte actually NVMe.
6 terabyte NVMe and how much RAM? How much RAM?
755 GB.
Okay, yeah. So 755 GB. Not like 3/4 of a terabyte, not fully a terabyte.
But it's like because of this round robin, the double buffer thing, we never keep because we discard. We have a continuous stream of new data, and that's why we don't even do validation because the model never well, at least I never look at validation because the model always sees new samples. And performance on synthetic data does correlate with performance on data.
So long as it's being refreshed. Yeah.
Yeah, that's what I'm talking about, right? So like you don't need a MongoDB in the middle. You can just if there's something that allows you to transfer the data from the writer directly to the reader, and you know, it should be faster, right?
Well, for us, it's an engineering choice. We want to minimize what we need to take care of. Consistency and all of these things. We know it's like rock. There's a thing with multiple years of engineering, and it's a marvel of engineering. Why would I solve, I just don't want to reinvent the wheel.
Also from the perspective of the training job, if you take away a central point where correctness is defined, which is the read collection in Mongo, you've now introduced n points of failure in the system. That is each of the generators.
And like one quick question, Raj needs to go anyway. And
Yeah, 5 minutes.
But since this is a master's thesis, we don't need we don't need to hide and discuss usually.
I don't think so. There's plenty of
people online are worried. They want to know what happens. What's the end of the story? Pass or fail, basically.
Yeah, I mean, we can on the face we can vote pass.
Okay. Wonderful.
Usually we have a secret vote, but But I think, like I observed, really there are two theses.
Yeah, because
there's the building of the environment.
You're okay.
I have I think this is very, you know, as a master's thesis, I think it's pretty impressive. You know, a lot of work.
Thank you, Dr. Ren.
Okay, thanks online people. Now you know the end of the story. Mike defended. Hooray.
Yay!